Hello everyone, I'm Hashalika Basawa, currently pursuing my Masters in Computer Science at Wichita State University. So I have done a project as part of my Applied and Practical Data Science course. So let me start presenting. So I'm excited to present you our project titled Optimizing BGP Route Selection with RNN. RNN refers to recurrent neural networks. It's a machine learning approach we have used to enhance the network performance. So before we begin, let me introduce my teammate Kota Tarun Reddy, who have worked along with me on this project. So to outline this presentation, firstly we'll start with the introduction to the Border Gateway Protocol, just a little brief about it, and then we'll see the project roadmap, how it is structured and the sequence that we have followed while doing this project, and then the dataset explanation, so the networking related information uh, that was given to us, and then we'll be pre-processing the dataset, which is the initial step of every data science project, and let's perform certain analysis on the data to gain an insightful information that would help us in feature engineering process. As we have decided on RNN model training, uh, we'll be training it, and then we'll evaluate the model performance. Finally we'll see the results and we'll see the conclusion. So to begin with, introduction to Border Gateway Protocol. So this will enable exchange of routing information between different networks or autonomous systems we can consider. An autonomous system is a network or a group of networks, so over the internet. So on internet, each and every network is given an autonomous system number, which is a unique identifier. So let me take an example. There is Comcast, an ISP, Comcast, internet service provider, which will be given an autonomous system member which can be used to uniquely identify Comcast globally. So where are these autonomous system numbers coming from? So these autonomous system numbers were assigned by IANA, Internet Assigned Numbers Authority, which will assign these AS numbers to the networks. Where can we use this autonomous? What are the benefits of having an AS number? Is it will help making routing decisions. It will also be useful while giving routing preferences of which route to be selected, and also we can filter. Routing filters can also be added, and also we can enforce certain policies based on the AS number. And it is like backbone of internet routing, we can say, the Border Gateway Protocol, and it is also responsible in determining the best path to be taken while transferring data from one node to other node. So objective of our project is to optimize the BGP routing decision using RNN model. There are multiple models in the market, but we chose RNN. We thought it would be the right fit. We have also done certain R&D or trial thing with the random forest model as well. We thought RNN would be the right model to do it, so we have switched to RNN. And then this will also help us understand how traditional BGP routing protocol is working and how our model is going to predict the optimized path when given information. So this is to improve the network performance metric, like we have latency, packet loss, route convergence time, and everything. So let's see the project roadmap. Part of our project roadmap, we have like 6 teams who are working on this project, and each team consists of 2 members. So week 1 we have allocated to start with the data collection and pre-processing step. So we were provided with the data set. The week 1, the team 1 is supposed to do this activity, and then followed by exploratory data analysis in week 2, and performance metric and traffic pattern analysis. So based on the data given, we thought of going for the performance metrics, like considering latency, packet loss, link cost, everything. We have performed certain analysis on it, and also the traffic pattern, at what time of the day the traffic is high, and for which application, for what type of broadcast it is high. So we have done certain analysis on that as well. And then as part of week 4, it is routing protocol state information analysis. So there is this precedence order given to AS path, next hop. There are certain metrics, key matrices that are considered for BGP. So for that, there is certain order of weightage given to each metric in order to train our model, so that our model assesses based on the network preference order, metric preference order we have given. And next, coming to week 5, it's feature engineering and model selection. As I've mentioned, we'll select the features based on which we want our model to get trained, and we'll also select the right fit for it during week 5. And coming to the week 6, it's the model training and evaluation. We'll also come with certain enhancements of our model, like hyperparameter tuning, and also to enhance, is there any change we can do in the metrics preference order we have taken previously. So we have done certain things during our week 6. So what we have gained through this is all teams have to communicate with each other in order to reach the ultimate outcome that we are aiming for. So it was a so let me explain the data set. uh, Let me quickly show you the data set. So here we go. This is a data set, and the node ID you are seeing, it is a unique identifier. It can be any device. In our case, these are the routers. If we consider the networking perspective, a node ID can be of a device like switch, router, load balancer, or anything that's related to network. So here these are the routers, so you can clearly see the naming on each router, like each node ID as router 2774. And then link cost. Coming to link cost is the numerical value given to the route, from the node ID to the next hop out router which it is going. That is the link cost between those two routers. And next we have latency in milliseconds. So this is the time taken for a data packet to traverse from the source to the destination. Coming to the packet loss, this is percentage of data packets that were lost during the transfer of data from the source to destination. Bandwidth is the maximum rate of data transfer through the network connection. It is measured in megabits per second, as you can see. And next we have traffic volume. This is the amount of data that was traversed during a certain period of time. And you can see application type, what type of request it was. It was HTTP, hypertext transfer protocol. It's like for web applications or something. And then at what time of the day this data packet transfer has happened. And this is the AS path. As I've mentioned, it is an autonomous system path number given to each network. And coming to the network prefix is to which network ID it is traversing to. And this is a next hop IP address is now, it's like next hop router. And we have security events, like if there is any cyber attack or any breach happened, then this says yes or no for it. Next, coming to the environmental factors, there are multiple factors like we have flooding, power failure, high temperature and all. So this is a data set which we are going to work on for this project. So as I've given the overview of data set, these are the categorization of the column values we are having with us. So the size of the data set is, we have 10,000 rows with 14 columns currently. And next, as part of our data set pre-processing, there was a column which was named unnamed 13, which has all null values. So as part of our dataset pre-processing, we have removed the column that has null values, and then we have addressed the missing values. So far we didn't find any missing values, so that's a good part. We don't have to spend much time in pre-processing data. And we have normalized the data for uniform scaling across features. So let me quickly show you the file as well, the running code. So this is the data set that we have taken. We read the data set into a data frame, and then this is the information. This is a column, unnamed 13, which is having null values has been removed. And we have checked for if there is any missing values across the data set. And we have cleaned it. As security event is something that doesn't add much value to our project, so we have ignored that as well. We haven't considered that for a further analysis. Moving forward, so we have cleaned our data set, and next step as mentioned. So what was our goal in this dataset pre-processing is to ensure a clean and consistent data for our further analysis. So let's begin with exploratory data analysis. So what we have done as part of our exploratory data analysis is, Uh, we have plot a correlation heat map which will tell how strongly or weakly two different parameters are correlated with each other. So as part of this, we have understood that the latency is inversely proportional to bandwidth. Latency is the delay and bandwidth is a maximum rate that can be transferred between source and destination. So we also have understood there is a high packet loss during the peak hours, I would say. When there is a lot of data transfer, there is a high chance of data being lost. So as part of this, we have performed the correlation heat map. Let me quickly show you the correlation heat map. Yeah, it's over here. This is our correlation heat map that we have plotted for it. And we see there's a weak correlation between features. We identify that whatever trends being shown were the ideal way the factors were associated with each other. So we thought we'll go for a principal component analysis of combining two or more features resulting in dimensionality reduction, which might help us in further analysis or to make the model much better, I would say, in terms of combining 2-3 features. It would help in predicting in a better manner. So we have done that. We also did outlier detection to understand if there are any outliers in the data set we are having. We found no outliers. And this is a trend line that we tried plotting between the latency. Latency refers, as I've mentioned, it's a time taken between the source and destination, right? So how is the link cost being affected with the latency? So this is something we have plotted. And moving forward, let me show you the PCA part for this. So we have considered two PCA components based on which we have done plotted a correlation matrix with the PCA components. And here we have seen that the PCA component 1 considered is positively correlated with packet loss with a 0.658 and the bandwidth for 0.51, indicating that it captures trends in network performance. And coming to the PCA 2, the component 2 that we have considered is negatively correlated with traffic volume, showing minus 0.67 as a value and minus 0.63 for the link cost. It reflects that it's focused on the traffic and link properties. So these are something, the actionable insight that we can consider from this principal component analysis is that high variance metrics like packet loss, traffic volume, bandwidth for predictive modeling are suitable. So this is something that we have got out of our exploratory data analysis. Moving to the performance metrics and traffic pattern analysis. As part of our traffic pattern analysis, we have tried finding out which application type at what time of the day is being used mostly. If you consider in real time, let's take an example of Instagram. If you see at the peak hours, Instagram's peak hours are like 6 to 10. It's like the usually free time people get in the evenings where they use social media a lot. So Instagram's views would be more during this period of time. Like that, it happens to each and every application. Consider YouTube. Whenever they are free, they'll watch YouTube. So there will be more further video streaming at that point of time. So for this, we have done certain analysis. So frequent hops, this is yes, and application type and what time of the day the application is being. So based on analysis, we found out that there's a lot of file transfer happening during afternoon. This is the average traffic volume and that's the total traffic volume. This is purely based on the data set we have. And next, to conclude, we have like FTP and video streaming dominate traffic during high activity times like nights and afternoons. So this will obviously impact latency, like the time taken to travel from source to destination for the data packet, and then the bandwidth. So gaming has also optimized performance metrics in the morning times, likely due to low network congestion. So this was done as part of a traffic pattern analysis and estimating the performance metrics. And coming to the protocol analysis, we didn't deviate from the traditional way of taking the precedence order for the key matrices of BGP protocol. We have gone with the same. The next step in this is feature engineering. So as part of our feature engineering, firstly we have found out the interquartile ranges. Based on that, we have done certain calculations on that, and we have come with the selected features. Let me show you. So if you see, yeah, we have done initially, we have corrected certain data types. Yes. So feature and the importance is something that we have plotted. So this is a PCA1 which was positively correlated that we have considered for our further analysis, right? So this is the order we have given, importance order, to for the features so that we can train a model. So the selected features are from the network topology. Node ID is your unique identifier that we have in our data set. The link cost, also the performance metrics such as latency, packet loss and bandwidth, as we are aiming to optimize the data transfer between two routes or else from the source to destination. So the routing metrics are like AS path and X hop were considered, and the traffic volume is also one of the key metric we have considered while training our model. So this will enhance the model's ability to predict the next hop IP address or else the next hop device that it has to take to reach the destination as quickly as possible, or else the optimal route selection happens. So the next step is training our RNN model. So coming to the RNN, it is an artificial neural network which is designed to process the sequential data. How RNN works is like the input given, it gives an output, right? This output is all fed to it, to the model, as input for the coming up thing. So it is like sequentially it remembers whatever happens. It's there. The output of your first input is stored to the model. It was trained on it again. So this is how it happens. It recognizes the patterns over time by maintaining that information of the previous input and output that has come. And the model architecture for our project is like, as I mentioned, RNN. This allows the networks to capture the temporal dependencies in sequential data. And this is trained on sequential BGP metrics to predict the optimal routes. So moving forward for the model evaluation, so the performance metrics considered were latency, packet loss and route convergence. So as part of this, we have understood the model performance has been improved, suggesting that the predictive model can reduce latency in routing, and also packet loss. Prediction metrics were also increased by training the model. Uh, And coming to the challenges faced, we had certain difficulty as we were during our initial phases. We didn't have the whole routing table information which we have to proceed with without having the data. But later point of time, we have got that data too, which was beneficial for us as well. Um So the final results of our project. Before going to the final results, let me quickly show you the model. So as I mentioned, initially we have done using the random forest model. So this is the code for that. And this is the partial dependency plots that we have plotted. And this is our final model using RNN. We have imported all the necessary libraries from the TensorFlow library. And here we go. So the performance metric, if you see trail 10 is complete, we have started tuning it. And the performance metric, if you see the validation loss, the latest was 0.08, but the best so far was 0.08 that we have got. So it minimized the validation loss, indicating effective learning and convergence toward optimal performance during training. So retrieving the best model. So if you see this part, the root mean squared error, So the model loss of data during training, the model achieved a loss of 0.08, indicating convergence and optimization success. The mean squared error indicates how well the model generalizes the unseen data. So our model is capable of answering to the unseen data as well, not just the data that we have fed to it. If we give some news data stating this is my source and this is my destination, so what would be the optimal path that I would take to reach there? So that can be stated by our model. Our model is able to give the output for that. So what's the outcome? I would say the final result is we have tried to a certain extent to optimize the BGP routing decision. This is purely based on the model output. In the practical practical or real time, if we consider, it takes time because BGP protocol traditional approach is different. This is just we are applying some machine learning algorithm to understand how it can be improvised or how can we leverage the existing matrices in such a way that it can make the protocol work in a better way. And there's one more thing I just forgot to mention during this. There is one local preference number, which is a key metric which was configured at each and every autonomous system level or at a router level, which gives or states that which route to be taken in order to means preference order you can consider. So that's something. And future scope of our project would be we should test it with a real world data set, as the current data set is also something that we have taken from the real time data, but still it has to be trained on a huge or humongous amount of data in order to get the better output or better results and trustable, I would say. And we also have to extend the model to predict network failures or to optimize under additional constraints as well. So our model should be capable of telling the drawbacks as well to while telling the optimal path. The conclusion. Uh, so I would like to tell, as part of this project, I've learned so much. We as a team, we have developed many interpersonal skills or behavioral skills to understand how it works on a real corporate world, how people deal, how people interact in the projects. So this course have benefited me in understanding how corporate works and how you can use machine learning to leverage things that happen in real time. And also we have achieved or tried, I would say tried rather than achieved, leveraging BGP using machine learning algorithms. And also related to project, I would also say we have improved performance metrics like latency and packet loss and the preference given to them, considering giving them the utmost priority. We have tried to find the optimal path. And I would like to acknowledge, uh, I'm very grateful to work as a team with the whole uh, teammates, I would say, from all other teams as well during this project. And special thanks to Professor Sai Karthik, who have given us invaluable guidance and support with all his expertise during our project journey. Thank you so much.